All right. Hey, everyone. It's good to be here at Open Source Week 2021. I'm Anders Eknert. I work for Styra. And today we'll be talking about the evolution of access control, identity and authorization in distributed system. But first, some words on me. Again, I'm Anders. I work as a developer advocate at Styra, which is the founders of the Open Policy Agent project. I have a long background in software development, primarily in identity systems. So a lot of users, roles, permissions, things like that. This is my third year working with OPA. Before I worked for Styra, I worked for a company where we integrated OPA into a distributed environment. So there will be a lot of talk about that today, kind of reflecting my experiences from that period. When I don't work with OPA, I enjoy cooking and food, and I'm a big fan of football. And I'm available on social media, Twitter, GitHub, LinkedIn, just my first name followed by my last name. So what we're going to talk about today is like the transition from a monolith architecture and into a distributed one, and what kind of implications that has in terms for authentication and for authorization. So of course, the responsibilities of the monolith application and the microservice application or the distributed application is basically the same. What the big difference is, of course, the way these components communicate with each other, where we see network calls rather than function calls. But we're not going to cover the monolith versus the distributed architecture today. Of course, we're going to zoom in on two areas of interest for us, and that's authentication and authorization. So the monolithic architecture provides a very simple way of dealing with things. So the monolith model, the application, it handles everything. So that includes authentication and access control. The user authenticates in the application, provides the credentials directly to the application, and a session is established. And access control, that was commonly performed inside of code, like application code. And normally you'd have a database with permissions where the application would go and do a lookup. The distributed model, though, authentication is commonly delegated elsewhere. So the application no longer communicates directly with the user database. And that's good. But up until now, the model for access control and permission has largely remained the same. And authorization often still lives embedded in code. And permissions are also retrieved still from external data sources. The problem, though, is this model doesn't really scale, and it turns out to be pretty difficult to manage, since if we increase the number of services and applications, they all depend on this permission store. So if we were to kind of apply a monolith architecture, but using microservices, that would be a pretty naive architecture, but it might look something like this. A user would present their credentials, and all services would need to verify the user identity, of course. So when they're presented with credentials, they go to the user store and check, is this a valid user, and so on. And all services, additionally, they need to check for permissions. So once the identity has been established, then we need to check, is this request allowed or not? And as you can see from all these arrows, this clearly doesn't scale, because these requests, they need to be synchronous. We need to wait and know before we send the request onwards. We need to know that this was a valid user and that the user and the request was allowed. So some problems here. The first problem is obviously that credentials are passed around between services. We'd rather avoid having user data, like passwords in particular, passed around between services. That should not be a concern for our services. And another problem, all the red arrows here pointing to the user store, that all these services, they need to do lookups to verify the user credentials. So solution here would be to delegate authentication to an external system. So as you can see to the left here, we kind of moved the user database outside of our cluster, and we let an external identity system handle that. So the user presents their credentials to the identity system, and in return has a token which it can then present to our services. So we've made an improvement. And of course, this is pretty much what Oauth is about. So Oauth provides us a flow or many flows for having token issues and having tokens like transported across our services. And then eventually OpenID Connect provides an identity layer on top of this, because Oauth doesn't really say what is a user. It's more or less just a subject. So OpenID Connect kind of standardizes that, allowing for federated identities. But again, Oauth doesn't specify what a token should look like. And if we were to run with something like opaque tokens, where you just have an opaque identifier like ABC123, when one of our services is presented such a token, it doesn't really know what to do with that. It would still need to do a lookup for in order to know, is this a valid token? So JSON Web Tokens, they can allow us, since they are self-contained, so they contain the data we need for the client or the user or the caller, and we can simply verify the signature of the token, and we can say that these claims they identify the user based on this identity system. So the identity problem is largely solved. We now have a secure and we have a scalable model for transferring identity. There's no more of these lookups to the user store. But we still have all these red arrows pointing to the permission store. So each service, they still need to check for permission. Even if we know who the user is or the client is, we still need to know, are they allowed to do this or not? So while we did solve the identity problem, we still see authorization becoming a bottleneck. Another problem is these systems, these distributed systems, they're often heterogeneous, meaning they include a lot of different languages, frameworks, and so on. So we don't really have a common way of doing authorization across the stack. So what do we want then? Well, some ideas would include this. We want to minimize latency. That's super important in these distributed systems. Since there's going to be so many services, we'd rather not have all these lookups taking place all the time. So authorization decisions should be made as close to your application as possible. And we want to avoid calling an external permission database in each service. As we saw, this is expensive and it risks creating a bottleneck. Ideally, we'd like to decouple authorization code from application and business logic. Because again, modern microservice architectures, they're heterogeneous. They include many languages and frameworks. And ideally, we'd like to do updates of authorization policies. If we add a new role or maybe a new resource type, we don't want to have to make that change in code and redeploy all of our applications or services. We'd rather have policy lifecycle live independently of application lifecycle. And additionally, it should be possible to share authorization policies across teams, across services, even if one of them is using like Python, the other one is .NET or Java. Ideally, we should be able to share the same type of authorization policies, so we can kind of audit and know that the same type of policies is enforced across our whole cluster or across our whole stack. And this is really what Open Policy Agent does. So OPA, or Open Policy Agent, or OPA, which is it's commonly pronounced, it's an open source general purpose policy engine. And what OPA does, it decouples policy from application and business logic. So sort of like the same thing the same way that a database decouples storage from your application, you can think of OPA in the same kind of sense, that you move out your authorization policies and move them into OPA. So you decouple that from your application. So ideally, your application is not necessarily aware that there is a user or that there are permissions. If you reach that state, you have successfully decoupled policy from your application and business logic. And another thing with OPA, it decouples policy decisions, but it separates decisions from actual enforcement. So your services, they still do the actual enforcement, because how your services choose to enforce these policies, that's still highly context specific. It could be returning a 403 forbidden header. It could be sending an alert to the security team or whatever. So OPA doesn't really do the enforcement. It makes policy decision and your service still acts on that. So what OPA offers is a unified way of dealing with policy across the stack. Again, in this heterogeneous environment, we don't want 8 or 9 different ways of dealing with policy depending on what programming language or what framework you choose to use. We want one way of doing it. And the way OPA achieves that is through the declarative Rego language, which we will look at in a bit. And again, since OPA is a general purpose policy engine, it's not limited to like service authorization, but you can use it for pretty much any type of policy. So that could be app authorization, Kubernetes admission control, data source filtering, CI/CD pipeline policies, and yeah, pretty much any type of policy. As for the OPA project itself, it's a pretty vibrant community. We have over 200 contributors to the project. There's over 50 listed integrations, almost 6,000 GitHub stars, 5,000 Slack users, and over 100 million Docker image pulls. So it's starting to be a really big project in the policy space, or even in the security space. And the ecosystem includes not just OPA itself, but also projects like ConfTest, which integrates OPA and uses policy to test things like configuration files and resources stored in files. There's the OPA Gatekeeper project, which is kind of tailor-made for the purpose of Kubernetes admission control. And there's also plugins for popular editors or IDEs like VS Code and IntelliJ. But of course, OPA is not just an open source like hobbyist project, but it's actually used by some of the largest organizations and companies in the world. And finally, if that wasn't enough to convince you, I think this quote from Kelsey Hightower kind of sums it up very nicely. The Open Policy Engine project is super dope. I finally have a framework that helps me translate written security policies into executable code for every layer of the stack. So that's pretty much what OPA does. So if that's what OPA does, how does it work? The way it works is basically through the policy decision model. We talked before about services, and in our case, in the distributed case, that might be a microservice, but the service in the OPA sense could really be anything. It could be the Kubernetes API, it could be a Kafka broker, it could be a Kong API gateway, or Docker, or a database. So a very broad definition of service here. But anything that services request. So when a request comes into that service, it sends a policy query to OPA. So what we want to figure out here is, should this request be allowed or not? So rather than trying to answer that itself, the service delegates that responsibility to OPA. And it does that by sending a policy query. And a policy query is pretty much any JSON value. So it could be like the name of the user, the path of the request method, or whatever. And then OPA, based on policies and data provided beforehand, can make a decision. And it responds with a policy decision. And this could often be like yes or no, or allowed or denied, but it could be any JSON value. So you could have like a nested object or a string, or maybe a reason why the request should be denied. So if we take that model to the distributed system we previously looked at, it might look something like this. We attach an OPA agent to all services. And when a request comes in with a JSON Web Token or some other way of proving identity or providing claims to the service would then query OPA to see should this be allowed or not. So OPA is deployed next to each service, and in the Kubernetes case, this is of course what we call the sidecar model. But we're certainly not limited to Kubernetes. OPA can run next to any type of service. And authorization decisions now live in OPA. They no longer are coupled to the application logic itself. And these services, normally they communicate with OPA through the OPA REST API. But there are some other options available too. If you have a Go application, you can use OPA as a library. If you're using Envoy or Istio for service mesh, you could connect OPA to that. There's also the option to compile your policy as WebAssembly. So if we were to look into the policy part of OPA, the Rego part, what would that look like? What does a policy look like? And what is Rego really? Well, Rego is a declarative high-level language, policy language used by OPA. So it's not like a general purpose programming language. It's tailor-made for policies. And a policy, just like a real-world policy, it consists of a number of rules. So it kind of tries to mirror a real-world policy. And rules commonly return true or false. Are you allowed or not? But again, we can be more flexible than that. And providing things like the reason why something was denied, maybe a list of obligations, and so on. And with Rego comes over 150 built-in functions to help you with policy authoring. So it has support for working with JSON Web Tokens, verifying identities, working with strings, roles, and so on. And since Rego and OPA treats policy as code, we can also test policy in isolation. And OPA comes with a built-in unit test framework. So we can test our policies just as like if there was if they were any other type of code. It's a well-documented project. So check out the official docs. I think they're a great resource as you learn. Additionally, there's the Rego Playground, which is a resource where you can try it out, where you can try policy authoring with Rego and OPA without even downloading OPA. And this screenshot here is actually from the Rego Playground. So just to give you a bit of a glimpse into what a Rego policy might look like. So first off, we have the package name. And a package name or a package is pretty much like a module or namespace from other programming languages. So there's not a whole lot to say about this. In this case, we just named it play. And next here, we see some rules defined. And in this case, we have a single rule, and it's called allow. But it's declared in many places. The first place, we say that if we don't know what the value of allow is, it should be false. So that would be the default value. So if we, for example, don't provide any input, or we're missing some attributes in the input, the allow should still evaluate. It should just be false. So that way we can ensure that there's always some response from OPA to the client. So we have an allow rule, and as you can see, we declare that on 2 places. So that means that if either of these conditions or either of these rules are true, we say the allow rule is true. So we can have as many of these allow conditions as we wish for. And if one of them, so it's an or between the rules, if one of them is true, allow is going to be true. So that is really the head of a rule. And inside these curly brackets, that's what we call a rule body. And the way it works is that if all the conditions inside of the rule body are true or evaluated true, then the rule itself is true. So if we check the first rule here, we can see that we iterate over the roles provided in the input. And if one of them is equal to the user admin role, we can see that this rule would evaluate to true. And we'll go into the details of each here. So what we can see here in the first case, if we were to evaluate or iterate over all the roles provided in the input, as you can see to the right here, we see that the user here provided in the request, they have the info role, they have a cube admin role, and they're also a Postgres DBA. But they are not a user admin. And we can see from the request path above there that this is a request to the user's endpoint. So if they were to be a user admin, they would be allowed. But in this case, they're not. So if we continue down to the next allow rule, we can see here the first condition is we're going to check, is the input method of the request put? Meaning someone is trying to modify a user here. And yeah, that's true. So we're going to move on to the next line. And on the next line, we're going to take the path provided in the request, and we split that. And split is one of these built-in functions provided to us from by Rego. So we're going to split the path on slash, and then we're going to use those path components. And in the first line here, we check that the first path component, the first one after the first slash, is equal to users. And that's true. It is. So we can move on to the next line. But here, however, we run into problems because we can see that what we do here is we check the second path component. That's the name of the user that's being modified. And on the last line of the policy or the last line of the allow rule, we compare that to the name provided from the user. And in this case, this is Alice. So Alice is trying to modify the Bob user, which she's not allowed to do. Alice can only modify the Alice user. Well, that kind of makes sense. So that's how you read a common Rego policy. So it's not that hard. And of course, in this case, allow would evaluate to false because none of the allow rules evaluate to true. So that's really a policy decision made by Oauth. Okay, so finally, we have data. Because in addition to policy, Oauth commonly needs data to make decisions. And this data, it could really be anything. It could be things like roles, the list of users, or any resource available in the system. Any data that's needed for policy decisions. And rather than having Oauth reach out to the permission database, as we saw in the old model, this data is provided asynchronously. So it's not queried at the time of the request. There's no latency added to the request in order to do lookups. So it's a model that scales for a distributed environment such as this one. So where do we get started? If you want to get started with Oauth, I'd suggest just start small. Write a few simple policies, a few unit tests, and try it out. Browse the Oauth docs. Again, they're a great resource. So get a feel for the basics and the built-ins and just play around. And once you get a basic understanding of Oauth and Rego, start to consider possible applications near to you. It could be previous apps or libraries you've been working with, and start to consider the information, the informal policies it dealt with. And after that, you can start to delegate some policy responsibilities to Oauth. And again, you don't need to start rewriting your whole app. You could start at a single endpoint or maybe a single role, deploy that, build experience. And once you pass that stage, you can consider scaling up. Oauth provides a lot of management capabilities for decision logging, providing policy and data as bundles, and so on. There's also the Styra Academy, which is a great resource for learning Rego. And of course, there's the Oauth Slack, where you can ask any question you want and take part of the larger Oauth community. So that I say thank you.